Sup, fools? Let's talk about Goroutines. If you're interested in Goroutines, it means you're a cool person. I just said it. All right, here are the topics. I have a little project going on the right hand side, and I've got some topics on the left. These are going to be the video chapters. We're going to go through all this. Let's start off with a demo. So if you go to smoothcriminal.mikedl.com, you just give an arbitrary numeric ID here, and this will create a fake job with ID 56, and what we can see here is that there's this web server that's launching. I'm going to tell you what's happening. It's launching a backend job, and the backend job is streaming its progress to the web browser. There's a WebSocket that's being fired up when you come to this URL for job 56 up here. There isn't like a record in a database somewhere with ID 56. That's just what I passed in at the beginning. So anyways, like it pretends like, oh, I've got job 56 to go work on. And then it comes in here, and the backend job is pushing its information through the WebSocket onto this browser tab. We can also go back, and I'm going to bring in another browser here. Same URL. I'm just going to copy and paste the URL that I get. So this is running, and if I paste it over here, we can see that this guy joins in, and the guy on the right, he gets all the updates that he showed up in time to get. And the progress bar, that went to 100%, even though he showed up late. So that's fine. Okay. I'd like to show the memory usage on the server. 5.5 megabytes for this Go executable. The code that drives this will be in the description of this video, so you don't have to watch it. Why are we going to use Goroutines to do this? Well, we have backend jobs. We're going to use Go to execute them in process. There are a couple assumptions. Like, what is a backend job? Like, why bother? Like, if you've got a lot of work to do, work that takes like more than 10 milliseconds, you probably don't want that in your web server. You want all of your like typical GET requests or even POST requests to be served right away. Like, less than 10 milliseconds would be great. Maybe much less than that would be nice. But if your process is, if you've got a lot of work to do, you want to like have that go in some other thread so that the web server doesn't block, and it gives the user some result right away. And then you can do what I just showed you. You can have a WebSocket connection that streams results from the backend process if you want. Like I really like getting streamed results from the backend job instead of having to wait whatever it is, like 15 seconds or 10 minutes to find out, hey, what happened to the thing I launched. With the approach I'm going to show, there's an assumption here that our backend jobs can run on the same machine as the web server. there's an assumption that if a job, if the server crashes, and we're gonna lose if this Go process crashes because I'm just launching a Goroutine to handle the backend job, that's gonna go down too, and we're gonna lose all memory of that backend job, which you might not want. I'll revisit that. There are Golang libraries that talk about how to set up backend job processing, and that's fine. You would probably consult those if you were preparing a production app. But like, the whole reason I'm making this video is to give me a reason to use Goroutines. Even if you are writing a backend job system separate from the web server, you'd probably want to use Goroutines anyway over there. And we'll see some at work here. The Golang features I'm going to use, we're going to have two interesting Goroutines, just two. We're going to be using channels. I'm not going to explain a channel from scratch. We're going to be using send, receive, the close built-in function, two buffered channels, but most of the channels we'll be using are unbuffered, and we'll be using Golang generics, kind of. They don't play a big role. So the app design, there are like a few things at play here. There's the hub, which is like this place where we can create subscriptions, and every subscription can have many subscribers, and you can send messages to a subscription, and that'll get broadcasted to however many subscribers are subscribed to that topic or subscription. And the hub is like a central shared memory location where we're going to keep track of all subscriptions and all subscribers that are paying attention to those subscriptions. Why don't I go ahead and get into the code here. We can see the hub here. We've got a subscribers hash or map. The keys in this structure are the names of the subscriptions, and then we have like some client information. Like there's an array of clients for each one of those names. That course, the name is the name of the subscription, and for each of those we get an array of what I'm calling hub channels, but those are basically clients. They're encapsulations of clients. We also have subscriptions. That's a map of subscription names to a simpler data structure. We're going to have a channel that's going to receive commands. The most interesting command is just the message command. There's a enum up here that enumerates all of the messages that I can send, the 4 types, and this is the main one. Like when we see this guy run, I'm sending these messages over and over and over to the hub, and it's broadcasting it to all of the WebSockets that are connected to the server. And then we also have a lock here that's for some critical sections, but that's we'll get back to that, but that's the hub. And I've kind of already talked about the subscriptions and clients. We have like the place where we use generics in this project is for communicating to the consumers or the clients of the subscriptions. So I have like a sendable type constraint, and I'm going to be sending whatever T is through this message channel. That's how I'm going to be sending information to the web browsers, which are the clients in this context. Again, the web browsers are making WebSocket connections, and by doing so, they become a client of the hub. But besides, like, what is the sendable? It can be a job status or a string. The job status is this struct, or you can just send strings. I can tell you that the web browser is using this struct. But my unit tests, they just use strings. It was actually, this took like about 15 hours of work, 15 to 20 hours of work. I found it difficult, but I didn't add generics, like the generic sendable, until the last minute. It took me like 30 minutes. It was really easy. That's a nice feature of Golang. All right, so if we go into the hub, there's this listen method here that is like, it's an infinite loop that the hub executes. It waits. The first thing it does is it just pops off a command from its feed of commands, and it says, okay, what did you ask me to do? If you want me to shut down, I'll go ahead and break out of this infinite loop, and I'll remove all subscriptions. That's here on 279. Do some cleanup. If someone's saying, hey, remove a subscription, it'll go ahead and remove just that particular one. We can also remove a subscriber, although I've found that in practice, I don't think this is actually getting called. And then there's the real like workhorse, which is the message. When I get that, I say, okay, give me all the subscribers for the subscription specified in this command. I check if the client is alive. If the client is not alive, I remove that client from my list of clients for the subscription. Otherwise, I go ahead and send it the message that came with this command. This is a channel that goes over to that client. If we go to the web server code, I think I need to, okay, that's fine. Like from the outset in my web server code, I create a hub instance here. My command, so I talked about a buffered channel earlier. Let me bring that up. This guy right here, the command channel, that's a buffered channel. I made it buffered because I thought it would help me with allowing clients to disconnect right away instead of having to wait for a web of channels to all get unblocked so that we could realize, oh, this client has disconnected. It's not really important though, this buffer size for the channel. But we instantiate it here as a global, and then here inside of main we call the init, which creates all of the channels so that they're not nil, and then we launch a Goroutine here for listen. So like when we get started, we start up the hub, and that goes off in its own Goroutine or thread, and then we can proceed with listening to incoming web requests. So that's how listen gets kicked off. The client threads, let's take a look at these WebSocket connections. For this, like, I don't really understand WebSocket, like the WebSocket protocol, not really. So I'm using the Gorilla WebSocket library. So this is the handler that serves WebSocket requests. we call this upgrade, which is a call to the WebSocket library, the Gorilla WebSocket library. If you don't like, I'm talking about this guy right here. So we get a connection from there, and then we get into an infinite loop where we say, tell the hub. Well, hold on, let me back up. Here we subscribe to whatever job is in the URL. So that's a method on Hub, and we get back a client, and we send a ping to let the hub know that we're alive, and then we pop off a message. We write that to the WebSocket connection. If we have an error, we go ahead and close our connection to the hub. This actually results in a close of the channel that we send our pings on. So if I go there, if I go look at this, this is the hub channel, is what we got back from the subscribe call, and we're calling close on it, and that just closes the client pings Golang channel. Yeah, this is a channel of empties. Empty is just this empty struct. An empty struct takes up 0 bytes in Golang, so that's why I'm using that. It's like the simplest channel you can come up with. And you can also see the body of is client alive. All I do here, sorry, that's the wrong one. Client ping, that's the one that's being called from the client. I just send along an empty instance. That goes to the hub. And if we go back to listen, we can see that they're going to check is client alive here. That's going to check the pings channel to see like, hey, did I get a ping from the client? Is client alive? Yeah, here's my client pings check. It does this idiom, which I hope you're familiar with. This returns okay as long as the channel hasn't been closed. So back to the right hand side, if we did get an error, we'll go ahead and close the pings channel. We also send a command to the hub saying, hey, please remove me. All of the subscribers have a UUID, so we go ahead and send that too, so that the hub knows who to remove. We do a non-blocking send here. If the command channel, if this particular buffered channel is full, it's not a big deal, because we did close our ping channel. And if we look at listen again, we're going to check that ping channel. So while it would be nice if the channel, if this channel wasn't full, then we could come in here and remove subscription, but that's okay. If it is full, we're protected here. We'll remove the subscriber here if we have to while we're broadcasting. I've discovered that this never actually happens. Like I thought that if I closed my browser, that this write JSON, that's the Gorilla WebSocket library. I thought that would return an error, but it doesn't. It's a place where we could improve things. And then if for some reason this message channel was closed, then I will go ahead and break from the infinite loop. And again, this where we're at on the right hand side is in the web handler for sending data to the WebSocket. Yeah, so it's pretty much just like ping and then where's my message, ping and then where's my message, ping, where's my message, and we just shoot them down the WebSocket connection. Okay, let's look at the JavaScript WebSocket. I don't use Emacs for writing client-side code anymore because Emacs support for TSX files, for example, is terrible, and its support for TypeScript isn't that much better. So this is the WebSocket handler. We just listen for the DOM loaded event. And then we launch all of these functions, but we're just going to concern ourselves with a WebSocket right now. So this says, hey, am I on a page that has this particular DOM element? And if you go to the basic, this is the non WebSocket page that you land on. If you're pointed here at this job 6, this is what you initially land on. And if we look at the template for this, there is a job container DOM element that's going to be placed in the middle of the page, and that's exactly what we're querying for here. So if we find it, that's how we know, oh, we have to come alive and start executing some WebSocket code, as the name suggests. So we'll get a couple more DOM elements, a little we have a add message anonymous function here. What's not really, what would you call this, a closure or something? I don't know. This just like does a basic append of text to a container. We extract the job ID from the URL, and then we go and connect using the WebSocket JavaScript class. We connect to this URL, and that's going to go to this stream job handler. So we've connected. We know that the hub is publishing to us. We're going to get things through our WebSocket connection, and we just send a message on open. And then when we get a message, we do a JSON parse. If we got a message of type message, then we'll go ahead and append that text. If we got a message of type complete, then we do a percentage calculation and set the progress bar equal to that result, and that moves the progress bar along. So you'll notice, like I said earlier, the web server is using the special struct here for sending out messages through the WebSocket, and this is our type that we're going to inspect here. We look for percent complete if we have a complete type, and if we have a message type, we just pick up the message here. I should be talking about the worker pretty soon. Yeah, so let me just finish talking about the WebSocket. The only other thing here is the close event. When I add a message for that. So if I were to just refresh this page, we would see that I'm opening and closing the WebSocket. There's no I guess the app is smart enough to not like, it's somehow figuring out that there's nothing to read. I don't remember like how I handled that, but the app is somehow doing it. Like this subscription isn't here anymore. Okay, so if I like the Running Job Goroutine, let's look at that now. Um, there's a create job handler, which is where things get started. So that's this handler here. It does a get subscription on the hub and says, hey, do I already have a job with this ID? Our I'll show you what the subscription names look like in a second. But if it can't find that one already exists, then it kicks off another Go routine. So this is the second Go routine that I talked about. The hub listen is one. The run job is the other one that is what I call an interesting Go routine. So it'll kick off that thread and then redirect to the viewing URL of the job, and that's what sends it off to the WebSocket streaming. But again, like this is the actual background job that's gonna do work. This job string is job colon some number. Like that's the number that you type in at the beginning of the process here. So it creates a subscription out of that string. It then does a loop of 15 iterations. It's doing a sleep in between each one, and it's telling the hub, hey, publish to this subscription the following message. So I go ahead and send 2 messages every 500 milliseconds. I'm saying please advance the progress bar. And this is a fraction of how close we are to the 15th iteration. And I also send a message that's just part I, where I is an integer hiking up to 15. And then when I'm done, I remove my subscription from the hub. So that's the background job. Kicking off the job, I kind of already talked about that. It's just this, like this is straightforward launching of a Go routine. This happened. This is actually a post. Like it gets mad if you're not making a post to this location. So it checks that, and then if we got like a real post, then it goes ahead and runs this. If we look at the index page that gets rendered when you go to the home page, we can see that we're going to issue a post here to this URL. So that's this guy that's being launched. All right, so I mentioned that the hub is a global variable. So I've implemented some critical section protection. This is in the package directory. I have a locks.go here. This is a if you Google Golang semaphores, you'll I think the third page down in the results set is a page that talks about easy semaphores using using channels. So I declare a semaphore here. It's just a channel of the empty struct. I think you can see that I'm defining empty to be the empty struct here. Again, it's a data structure in Go that it takes up 0 bytes in size. And I like using it instead of booleans because I don't actually have a true or false nature to this data structure. It's just like all I'm going to do is when someone calls P on the semaphore, I'm gonna stick something into the channel. This is in practice going to be a binary semaphore, so it's going to be a buffered channel of size 1. So this is going to succeed on the first guy who gets to the semaphore, and it's gonna anyone else who comes in is gonna block on that channel because it's full. And then you call V. This is P and V. That's like the classical methods on the semaphore if you read an operating systems textbook. So on the way out, we're gonna pop off the semaphore. That's gonna let the next person in line get in because they're blocked here, and that's our semaphore. There's also a read-write lock. I have 3 semaphores in this lock, and if we go and look at like how this is used, what we'll see, like if I go to remove a subscription from the hub, this is the implementation of that. This already locked is like kind of it's a distraction. Just pretend that these guards aren't there. The point is, if we're not already locked, we're gonna lock for writing. That's gonna call this guy. We call wait. P means wait. V means signal. We call wait on a service queue. That's also used at the beginning of the lock for reading. And then we call wait on the resource lock, which is the lock that's closest to the data we want to protect. And then if we get in and we go ahead and get out of the service queue, the readers, they'll line up at the service queue. If they get in, they'll lock a critical section to the number of readers. If they're the first reader, they'll go ahead and lock the lock around the sensitive data. They only do that if they're the first reader in. So you can have many readers use this lock for reading method, and if you've got like 4 readers, they'll all get in. And on the way out, they let whoever's in the service queue come in, and they release the reader count lock as well. The reader count lock is just for this variable in this lock data structure. So unlocking, if you look on the left-hand side, when we're done, we're going to call writing unlock. And if we return early because of an error, we need to unlock here as well. This this is lock for reading. Excuse me, I wanted to talk about reading unlock. Writing unlock is simple. We just get rid of the critical section guard. But if we're doing a reading unlock, we lock the count, we decrement it. If we're the last reader out of the critical section, we let go of the critical section lock, and then we release our grasp on the reader count. This algorithm is taken from the Wikipedia page on the readers and writers problem. It's pretty much the exact same thing. And I picked this particular implementation of the readers and writers problem because it doesn't starve the readers and it doesn't starve the writers either. Like, everyone has to start off at this service queue, so they all get in line and there's fairness. On that Wikipedia page, the first 2 algorithms have starvation vulnerabilities, which I didn't want. If you don't do this, you will encounter a crash that looks like this. I was running some tests and I got this ridiculous I just got a crash that said, hey, you're trying to do concurrent map writes. Like, we have a real global, so we have to be responsible in our use of it. If you're using a library, you probably don't have to worry about this because someone else has worried about it for you. So that was semaphores, the readers and writer lock. how channels help, I just wanted to mention that I do find the channels in Golang to be really nice for coordinating goroutines. If you didn't have channels, you would just have to reinvent them. Like you would have to have global data structures that are like queues for messages being moved around, and you'd have to add locks to those queues. And why bother? If you can just use Golang channels. I wanted to mention that for semaphores, I mentioned how this particular call on line 13, it'll make other users of the semaphore get in line at the channel. And there's an interesting question about this on Stack Overflow that I actually posted an answer to. Like, I wanted to know, is the order in which you arrive at the channel preserved when you start blocking, when everyone starts to block because it's full? I added this. This is my answer, and I illustrated what I wanted to say with the test. This is the same concept as what's going on in the code I showed you with Emacs. This is just a Golang test. I make a lock out of the empty struct. It's of size 1, and I have this add function that acquires the lock and then releases the lock after it's done doing a mutation to an array. What this test does is it staggers 10 goroutines. There's a loop here of 1 to 10, and it launches a goroutine of the I, where I is a hiking interval. If it's not the very last iteration of the loop, it does a sleep for 10 milliseconds. And then this add function, if I is 0, that means it's the first goroutine that got launched. It sleeps for 100 milliseconds, which means it's going to hang on to the lock. This is happening after it's acquired the lock. So it's going to sit there for 100 milliseconds. That means that all of these other guys are going to queue up. And finally, after it's done sleeping, it'll do its thing and release the lock. All the other goroutines will execute. At the end of this test, we just wait for they're inserting into this done channel when they're done. So we wait for the done channel to be closed, which happens when the last goroutine executes and finishes, and then we construct a string of everything that was added to the array. And if it doesn't equal this ordered string, it's like an ordered string, then we say the test didn't work. But this test passes, and I mentioned it here. It passes again and again and again on my OS X machine. It also passes on Ubuntu Jammy over and over and over again. So I believe the answer to this question is yes. If you look at this example, the answer to the question is no, because he's doing something a little different than what I'm doing with semaphores. Unit tests. So if we go to my package directory, I have some unit tests here, and I thought it'd be nice to show you one of my tests. Let's see. Listen. So this is one of my tests. I construct a hub. Instead of using the job status struct, this is a hub where the message type is string. That's a generic parameter that I'm giving it here. So I have a hub of strings, where what's the message type that the hub is going to manage? It's a string, because that's what I said here. So here I go ahead and kick off a goroutine that's gonna run listen, and then when it's done, it's gonna send an empty struct into G1, which is just a channel. Oh shit. I hate it when I do that. All right, where were we? I kick off listen here with this Goroutine, and EM is just a it's just an alias for the empty struct, which you can see here on the right. I have a couple of coordination channels. I have a job Goroutine that launches here. This is, if you've never seen it, this is just an anonymous function that's being launched as a Goroutine. So the job, this is like the backend job. It's going to create its subscription, and then it's going to send a message into the client Go channel, which is something. I have another Goroutine here, which is going to simulate the client that's going to use the hub. The first thing this client does is try to read from the client Go channel. So it's going to block, and it's going to block because I don't want it to do anything until the subscription has been created. So that's why I have this channel here. I thought this was like, when you get addicted to this, if you're writing unit tests, like how do you might say, like, how am I going to test my my parallel code? Like, oh my god, it's going to be the end of the world. I was able to do this, and where possible, I use channels to coordinate between my between my threads or Goroutines, like you're seeing here. So once the client gets going, or the client simulator, it's going to subscribe to that subscription or topic, and then it's going to send a message into the job continue channel. That's what the job Goroutine is going to be waiting for. And then once the client is subscribed, it'll proceed. It'll publish twice and then indicate that it's done running. What we see here is that the client is going to send in 2 pings and pop 2 things off of the message queue. It's ping and then read, and then ping and then read. It depends what it reads to this messages array of strings. And then we do an assert. This assert is provided by this library up here. Okay. And then we do one more ping because the hub is going to want to see that. It's going to go ahead and inform the client that it's done. I think it just closes the channel on its side. And then we send a message into G3, which is just a channel to say, hey, the client is done. So we wait for, inside of the outermost thread, the test itself, we wait for the job to be done. If we look on the left, that's happening at the end of the job Goroutine. We send the shutdown command to the hub, and then we wait for G1 and G3 to finish. G1 was the hub listen. So we wait for the hub to finish, and we wait for the client to finish. We assert that I've got no subscribers in the hub. So that's like the anatomy of a test that's using Goroutines to realistically exercise the code. I'm just gonna show that one example because I'm getting tired of talking. So I did want to mention that this was difficult. Like, as soon as I realized that I was gonna have to do critical section protection, which was at the beginning, I kind of thought, well, this is gonna take 15 hours of work, and it did, and it was tough. It's about 1,500 lines of Golang. most of the code is in my tests. If I do I have this little utility that counts up my lines of code, and we can see that my hub test is 721 lines, whereas the hub source code is only 309 lines. So that's, I think it's common to have like a lot of tests for your code because you want to make sure your stuff works. The unit tests were very valuable. I wrote the hub and the locks section first. Like this, I wrote my web server code last, and I wrote this hub.go and locks.go first, and I wrote tests for them. That was 90% of the work. The web server was like 10% of the work at the very end, not including the client side code that I had to write to do the progress bar effect and the streaming effect. But when I went to wire up the connection between the hub and the web server handlers, and for that matter, the WebSocket JavaScript, it worked the first time. Like I had to sort through some wiring bugs. I don't mean to say that I wrote everything perfect when I did the wiring. I didn't. I had to fix those bugs, but I didn't encounter any surprises on account of my hub code being broken. And the reason my hub code wasn't broken was because I had all these fucking tests to find the bugs before I started worrying about the web server. So that's like, I think we can always talk about the importance of writing unit tests. And in my previous Golang videos, I wasn't writing unit tests, not really, but for this project, I got into it. Okay, some concerns. I don't know if I'm going to spend much time on this. Job durability would be nice, so that if your jobs crash or if the server goes down, you still have your jobs in Redis or something like that. If you wanted to add that to this project without using one of the Golang libraries, I don't think it would be very hard. Instead of what you would do is instead of like launching jobs here, you would insert into Redis, and then you would have another infinite loop that just keeps checking Redis, some list in Redis for the JSON that you've pushed into it that represents the job. Like I think you would probably push in a JSON struct that says, hey, here's my input, and here are like here's the kind of job I want you to run. Like your app would probably have more than one type of background job, and so you could say, okay, here's my type and here's my input in a JSON struct, or like I think that would work. I think I broke my Emacs. Okay. Using Golang on a dedicated job server would probably be the way to go if you're writing a really slick app. I think it would still be nice. I don't know if I already showed. I think I already showed you that this was using like 5 megabytes, and so that memory savings is really nice compared to something like Ruby on Rails, or for that matter, like that. I bet you a lot of languages can't do this as well. This approach, like this idea where I'm just gonna keep on kicking off Goroutines every time someone comes in to launch a job, that's probably not how you want to do it. You probably want to have a fixed number of Goroutines that are listening to some channel to say, hey, it's my turn to run a job. I'd have to think about how to do that. What are you going to do about slow consumers? So if we go to the listen loop, we do this is client alive, which looks for a ping from the consumer. But what if the consumer is really busy? I say consumer, I'm still talking about the client or the subscriber. Like, what if they're really busy and they haven't sent their ping yet? Then you're gonna block, and none of the other consumers are gonna hear from you. You can work around this problem for a while by using a buffer channel. Like, say you have 256 openings available for a message, and then you could say, hey, I'm not even going to listen for pings from the client. I'm just going to keep sending into this buffer. You could use a non-blocking send, and then if you fail to push in there because the buffer is full, you can just kill the client to say, hey, you're taking too fucking long. I'm just not even going to talk to you anymore. I think that's probably what you have to do. Like, your clients shouldn't be if you have a slow client, you probably don't want that client to ruin everything for everyone else. And like, even if you're not using Golang channels, this problem still exists. Like, if every one of your client gets a buffer of say 256 message slots, and some client doesn't consume fast enough, and the buffer gets full, you have to make a decision in this part of the code that I'm highlighting. Like, what do you have a client and their buffer is full. Even if you're not using Golang channels, you still have to decide what you're going to do. Are you going to skip that dude and come back to it again? Or are you going to kill it? That problem doesn't go away just because you decide not to use channels. So it's just something to think about. And lastly, I come from a Ruby background. That means Ruby on Rails. The way to do background processing there, they used to have delayed job. I think Sidekiq is more common now. I've got this post open by Mike Perham. This is from last October. Sidekiq 7 came out, and he was like, hey, instead of needing a 500 megabyte Sidekiq process and a 500 megabyte Puma process, you can use embedding now. And you just read this and you think about the 5 megabytes that I showed you. Yeah, I know what I showed you doesn't have business logic yet, but do you really think you're going to balloon up to a 500 megabyte process the way Puma does? Like, you're going, the memory savings are like 1 gigabyte compared to something probably not that much higher than 5 megabytes. Like, that's what really excites me about Golang. That's the whole reason I made this toy project and this video. That's why I'm calling this Goroutine Propaganda. You have to live with yourself if you're going to write Ruby on Rails processes that are going to be this large. And I just think it's such an opportunity that Golang presents to us with its Goroutines. Like, look at how much smaller our processes can be. To say nothing about some of the other nicer things about Golang. The static type checker, for example. You could say, like, well, why wouldn't I just write threads in Ruby? If you're using Rails, you start in a controller action. You have no idea what the shared memory space looks like. Like, what are the globals? You don't know. Like, if you go and read the Ruby on Rails guides, you're not going to know. Like, that's not going to teach you. I've used Rails for a long time, and I don't know what's in the global memory space. So if you kick off a thread, like, how do you know what resources you can read from and not read from? How do you handle your critical sections there? If you're gonna launch a thread, do you join? Like, wouldn't you feel irresponsible launching a thread from a controller? Like, if you're gonna launch it but not call join, to me that feels really irresponsible. And I think this is part of the reason we don't use threads in Ruby. like not in Rails. Like they're still from that old way of thinking, which is that threads are really fucking complicated. But Golang says, hey, let's think about threads from the beginning. We're gonna have these primitives called Goroutines that you can launch really easily. So please go learn about them. It's a really different mindset. And then at the end of the day, you know, unless you're using JRuby, you don't actually get true parallel performance with Ruby anyway. Like the global interpreter lock is there, so it's not like your threaded code is actually parallel. I'll finally mention that my unit test speed, like having fast unit tests is really cool. Like I've seen some slow Ruby RSpec test suites, but if you're here, I got. Let me actually like show you all of the tests running. They go really fast. Like the first run there took me 1 second, but like I have a number of tests here and they're running really fast. I reckon that would be really pleasant. And that's the end of the topic list. I don't really have anything to say at the end of this. I hope you had. I hope you liked this. It's really manly to use Goroutines this day and age, and I would, you know, I'm excited about them. So I hope you found this cool.